So today, the question we have here, or the problem we have here, describes a second order control system. The system is represented by the transfer function, which is this Q naught of S over T of S is equal to 1 on JS squared plus Fs plus K. Q naught of S represents the output angular position. T of S represents the input torque applied to the system. J is the moment of inertia of the system. F is the viscous damping coefficient. K is the stiffness constant. Yes. These three parameters, J, F, K, determine how the system responds dynamically. The problem states that a step input torque 10 mm, 10 nm, 10 nm is applied to the system. When a step input is applied to a second order system, we can analyze its behavior using time response characteristics. Three important response characteristics are given, which is A, B, C. So we have the maximum overshoot, which is the MP given as 6%. We have the peak system, a peak time, sorry. We have the peak time, which is a TP, which is 1 second. And then we have the steady state error, which is zero point 0.5 radian. This tells us the difference between the desired output and the final output after the system settles. Using these three parameters, using these three performance specifications, we can relate the system to a standard second order system form, which allows us to determine the unknown parameters. So the objectives of this problem is to use the overshoot peak time and steady state error information to identify the value of the system parameters J, F, and K that define the system dynamics. I'll leave it for my partner to take over.
All right. So now that the question has been introduced, let us begin solving the problem. We are told that the system receives a step input torque of 10 Newton meters. And in control systems, when we work in the Laplace domain, a step input of magnitude A is represented as T of S equals A over S. And now since the magnitude is 10, the input becomes T m of S equals 10 over S. And then the transfer function of the system is given as 1 over G S squared plus Fs plus K. So to find the output of the system, we multiply the transfer function by the input torque. So bringing T of S here, we have 1 over G S squared plus Fs plus K multiplying T of S, which is giving us 10 over S. And hence, as we can see, we see 10 here, and then we see S here multiplying the denominator. So this expression represents the Laplace transform of the output displacement of the system. However, what we are interested in first is the steady state value of the output. And the steady state value tells us what the output settles to after a long time when the system becomes stable. So to determine this value, we use an important tool in control systems called the final value theorem. The next presenter will explain how this theorem is applied to determine the constant K. Thank you. Okay, so I'm coming to talk about using the final value theorem. Now, to determine the steady state value of the system output, we apply the final value theorem. The theorem states that limit t as approach infinity, q naught of t is equal to limit s approaching 0, s q naught s. Now, this means that the steady state value in the time domain can be found by multiplying the Laplace expression by s and then letting s approach 0. From the previous step, we obtained q naught of s equals 10 over s open bracket js squared plus fs plus k. Multiplying by s gives sq of naught s equals 10 over js squared plus fs plus k. Now we take the limit as s approaches 0. When s becomes 0, the terms containing s disappear. So the expression becomes 10 over k. So now the problem states that the steady state error of the output is 0.5 radians. Therefore, we set 0.5 is equals 10 over k. Solving the equation gives k equals 20. So the stiffness constant of the system is is 20. Now that you have determined k, the next step is to determine the damping ratio represented by the symbol theta here. This will be done using the percent overshoot formula.
So next, we determine the damping ratio, which is represented by the Greek letter zeta, which is this. The problem states that the system has a percentage overshoot of 6%. In control systems, the relationship between percentage overshoot and damping ratio is given by the formula, this formula, where MP is the percentage overshoot expressed as a decimal. So we convert 6% to decimal form. MP is equal to 0.06. Substituting into the question gives 0.06 with this, gives this. To solve this equation, we take the natural logarithm on both sides. Now, when we solve it, this is the process of solving it. Then applying and after simplifying and solving for zeta, we obtain this, which is 0.667. This value represents the damping ratio of the system, which tells us how oscillatory the response will be. A damping ratio of 0.667 indicates that the system is underdamped, meaning the system will oscillate between settling at its steady value. The next step is to determine the natural frequency of the system, which will be explained by the next presenter.
Okay, so continuing from where you left off, you were given the peak time, right? Which was 1 second. Now, in a second order system, the peak time and the damping ratio is related by this equation. And also, the damping ratio was given as 0.667. Now, substituting the damping ratio into the equation, we are going to have this equation. Now we can find natural frequency, which is going to be 4.21 rad per second, and then we can go ahead and find the rest.
So the next step is to compare the system equation with the standard second order system form. So we take the denominator of our transfer function, which is js squared plus fs plus k equal to 0. And then to make the equation simpler for us, we divide each term by j. So we have s squared plus f over js plus k over j being equal to 0. So the next thing to do is to compare it with the standard second order system equation form. So doing that, we take the last term, which is omega squared n, and compare to the last term of our denominator, which is k over j. So having done this, we make j the subject, and once we do the comparison, we find the equation for j, and then we call upon the next person to help us calculate the value for j.
To determine the moment of inertia G, we use the equation obtained from the coefficient comparison, which is omega squared n is equal to k, which is stiffness constant, divided by the moment of inertia. Omega n, which is equal to 4.21, we square it. This will give us 17.72. We then input it into the equation. That says 70 omega n squared is equal to k over g. After rearranging it, we get j is equal to k, which is stiffness constant, divided by the omega n squared. This leads us to the answer j is equal to 1.128. Therefore, the moment of inertia is equal to 1.128. Thank you.
To determine the damping coefficient F, we use the second equation obtained earlier, which is 2 times the damping ratio times omega n, which is equal to F over J. Rearranging to make F the subject gives us F is equal to 2 times the damping ratio omega nj. Now, omega is equal to 4.21 J is equal to 1.128, and the damping ratio is equal to 0.667, which gives us F to be equal to 6.34. Therefore, the damping coefficient of the system is approximately 6.34. And at this point, you have successfully determined all the unknown parameters of the system. The final presenter will summarize the results and conclude the presentation.
Conclude our analysis, we successfully determined the unknown parameters of the given second order control system. Using the final value theorem, we calculated the stiffness constant, which is equal to 20, and using the percent overshoot formula, we determined the damping ratio, which is 0.667. And using the peak time equation, we found the natural frequency, which is 4.21 rads per second. Finally, by comparing the system equation with the standard second order model, we calculated the remaining parameters. Moment of inertia, which is equal to 1.128, damping coefficient, which is 6.34. These values fully describe the dynamic behavior of the system. Through this problem, we demonstrated how classical control system tools such as Laplace transforms, final value theorem, and second order system relationships can be used to analyze real engineering systems. Thank you very much for watching our presentation.